Hello everyone, my name is Phil. I've been a college chemistry professor for over 40 years. I've studied climate change for the past many years. I'm offering my interpretation of the 42-page summary of the 6th Intergovernmental Panel on Climate Change report that recently came out, in case you are looking for something a little less intimidating. I used the figures from that summary in my presentation. The actual report was put together by 234 scientists from around the world and is almost 4,000 pages long and has about 14,000 literature citations. So it's quite a chore to try and understand all that's in there. My first slide here is just sort of a generic summary of written out information on pages 1 through 3 of the report. So they mentioned there the top 3 greenhouse gases are in 2019 are carbon dioxide, methane, and nitrous oxide. The ones most commonly talked about are carbon dioxide and methane. In the last 4 decades, we have the warmest recent decades of the recent recorded history, and each decade has gotten progressively warmer. If you want to go back to their reference time is 1850 to 1900 for many of the factors in this report. So their reference temperature back then, compared to what is now, the temperature increase in 2011 to 2020 decade was about plus 1.1 or so degrees Celsius. Now most of that was on land. It went up about 1.6 degrees Celsius, and in the oceans it was about 0.9 degrees Celsius. The warming factors add up to more than the 1.1 that you see there. They're between 1 and 2, and there's some cooling factors as well. These are the aerosols, mostly sulfur dioxide, and that takes the temperature back down. So if these were ever to be eliminated from the atmosphere, then the actual warming factors would display more strongly than they do currently. And that's a possibility if we eliminate coal, because most of the sulfur dioxide comes from coal. Global precipitation has increased since 1950, and it's going up faster since 1980. The storm tracks, typhoons and hurricanes and so forth, have shifted poleward in both hemispheres. Human influence is causing a retreat of the world glaciers, snow cover, Greenland ice sheets, Arctic ice, and so forth. But there's no definite trend in the Antarctic ice that's down there. That seems to be fairly stable. There are some opposing factors that's causing that. The upper oceans, that's to about 700 meters deep, have been warming since the 1970s. The oceans are about 30% more acidic than the previous millions of years, tens of millions of years, and getting more acidic. Sea level has risen about 0.2 meters since 1901, so that would be about the recent 120 years or so. So 8 inches doesn't sound like much, but from 1901 to 1971, the average rate was 1.3 millimeters per year. And you'll notice when we went from 71 to 2006, it went up quite a bit, about 50% increase, 1.9 millimeters per year. And since that time to 2018, it's gone up 3.7 millimeters per year. So you can see there's a definite trend towards increasing values with each interval. The climate zones in both hemispheres have been shifting poleward, so it's getting more warm as we move towards the poles than it used to be. And the growing seasons around the world have gotten about 2 days longer per decade since the 1950s. So I calculated that would be about 14 extra days of growing season. Now all the figures in the slides that are coming up are from the 42-page summary of the IPCC report. This first one looks at global surface temperatures relative to, again, this interval, this reference point, 1850 to 1900. So here they're going back to 2000 years to 0, and then so we see it's pretty flat. It starts to drop off a bit, and right here's where our reference interval is, 1850 to 2000, and you can see it's shooting up quite a bit according to the scale that we have here. This little bar on the left is the warmest century back to about 100, or actually 125,000 years. So this is like the warmest interval we've had in that time, and you can see we've already reached that in just a very short period of time here. This is expanded out a bit. This goes back to 1850, so we're looking at about 170 years here. Pretty flat, and they have 3 different lines. The black line is the actual observed temperature. So you can see it's pretty flat and then it's going up. The sort of brown line is the simulated temperature using human and natural influences in there. And you can see they follow very closely, so it's pretty close. And this is some error bars on the temperatures that they're measuring. If they take out the human influence and just look at natural only, you can say the the temperature stays pretty flat. So this is a difference attributed to human influence on the temperature of the world. Okay, so this is breaking the temperature increase down into different components. This is the actual temperature observed from 1850 to 2019, about 1.1. I put the numbers in there. I just interpreted the graph for you if you want to look a little closer and see if you disagree or agree with my numbers. You can see this is the overall result, but if we look at just the things that are the greenhouse gases, so that would be the carbon dioxide, the methane, the nitrous oxide, and so forth, it's more than 1.1. And that's because there's some opposite effects that are in there. These would be mostly the aerosols, mostly sulfur dioxide. And so that cancels out part of this, and that's why we see just a net result of 1.1. If we come over here, we break it down a little more. Here's the carbon dioxide influence. Here's the methane influence. And you can see methane's pretty significant. People almost always talk about carbon dioxide. But methane's coming on strong, and it's getting stronger over the years. And so this is a big concern because the methane's about 80 times stronger infrared absorber than the carbon dioxide. Although it disappears pretty fast within 20 years, it's almost all gone, although we continually release more methane out. These are some the nitrous oxides, chlorofluorocarbons that we have a little bit in, but they're very strong IR absorbers. But you can see they're pretty small compared to these guys. These are some opposing influences that actually cool the Earth. Nitrous oxide's pretty small. Here's the sulfur oxides. You can see they're the dominant feature here. Okay, some volatile organics a little bit. So there's some other stuff down here. We won't worry too much about it. You can look at that more closely if you want to. So some points to make around here would be atmospheric carbon dioxide concentrations are higher now than in the past 2 million years. Methane and nitrous oxide concentrations are higher than any time in the last 800,000 years, and they probably didn't measure them back beyond that. Global surface temperatures are increasing faster since 1970 than any other 50-year period over the last 2,000 years. And if you go back 6,500, that's how far you have to go till you find something like this type of an increase. And before that, then you have to go back about 125,000 years. So these are not very common that we're looking at, and it's happening way faster right now. The 2011 to 2020 Arctic Sea area has reached its lowest level in recorded history, which has been since 1850. The world glacier retreats since the 1950s are going faster than ever, and some of them have already disappeared. Okay. The global mean sea level has risen faster since 1900 than any preceding century in the last 3,000 years. So sea level is going up, and as I mentioned in the previous slide, it's going up faster and faster. Global ocean warming is getting faster also over the past century, more so than in the last 11,000 years. This is a little schematic of the world. Each of these little hexagons represents a region of comparable area, similar area. And up here we have the North American area, so this would be sort of northwest North America, northeast North America. This would be Greenland and Canada, Central America here, South America here. And if we come over here, this would be Europe, and this would be Asia. So they have North and South and East Asia. This would be Africa, and this would be Australia, New Zealand, Pacific Islands, and so forth. So what they're looking at in this particular grouping is the hot extremes in different regions of the world. And if you look over here, you see that this particular color means there was an increase, and it shows that 41 of these little hexagons increased in temperature. Some where there's limited data, so they're not actually saying there. And these hash marks are sort of a disagreement. They might also be warming, but it's not totally agreed. The little dots indicate sort of a confidence level. So more dots is more confident. So for the hot extremes, the evidence is mostly drawn from daily maximum temperatures. Other things they use are heat wave duration, frequency, intensity of heat waves, and so this just indicates the temperature's going up here. This little schematic, same idea: North America, Greenland, South America. Heavy precipitation in different regions of the world. Okay, and you can see it's not quite as uniform here. The increase in precipitation is in 19 of the hexagons. Decrease, no, none are decreasing. So then there's other ones that are sort of on the low end or not determined. And so this is the like greater amounts of rain and so forth, snow. Heavy precipitation evidence is mostly drawn from the indices based on the 1 day or 5 day precipitation amounts using the global and regional studies. Okay. In this particular schematic, we're looking at drought, agricultural and ecological drought. So I put down here agricultural drought refers to conditions that result in adverse plant responses, which can range from reduced crop and forage yields to total crop or forage failure. So this would be a decrease in the amount of crops grown. Ecological drought, episodic deficit in water availability that drives ecosystems. So we're not necessarily looking at crops here, we're looking at more like ecosystems. Beyond thresholds where you put the species, the organisms, in a vulnerable position. And some of these could trigger feedbacks in natural and or human systems. So again, increased drought would be the dark area, the brownish, dark brown areas. Limited data, sort of the purple ones, we don't know for sure. And actually there's a place where the drought is going down. So I would imagine that means more water. Now here's where they start to break up different scenarios. So they have 5 scenarios that they present in the IPCC report. They have funny names. They got SSP 5, and then you look for a 4. Actually, I think I saw a 4 in the report, but here there's only SSP 3, SSP 2, 1, and then they have 2 1s, and one is at 1.9 and one is at 2.6. So these are a little mysterious, these terms here. Now the SSP stands for Shared Socioeconomic Pathway, and then they have a number, and that numbers just indicate, is it 1, 2, 3, 4, 5. And then they have another number, and that's the approximate radiative forcing, and that's like the pressure on putting extra energy into the earth in watts per square meter. Now watts is kind of a mysterious number if you're not familiar with the science, but a watt is basically a joule per second, and joule is energy just like calorie. If you were eating food, you'd say how many calories are there. So joule is just a different way of saying amount of energy, and then per second is the watt. So every second that went by, you'd have a joule, a joule, a joule, a joule, and so forth. So that's a rate of energy transfer. And they use that to measure where the heat is going in the world. All right. Now, if it's a positive value, you're going to be adding in heat. And if it's a negative value, you'll be taking heat out. Now, I put in here the area of the Earth because I did a little calculation down here. I said, what if we put out 1 watt per square meter? Now, a square meter, that's about like a square yard. That's about the same area you would be standing in. If you just stood in a spot right there, the area around you would be about a 1 square meter. And so remember, the watt is a joule per second in that 1 square meter. Now, if I multiply that times all the square meters of the Earth, that would be 5.2 times 10 to the 14th watts. That would be joules per second. So in that moment, for the entire Earth, the Earth's putting out if we had 1 watt, it would be 5.2 times 10 to the 14th watts. Now, if we looked at it for the whole year, which is what they do a lot of times, then I'd have to multiply by all the seconds in a year, and that turns out to be 32 million seconds. So that would be a much bigger number. Just 1 watt, that's a joule per second. That would be 2 times 10 to the 22 joules coming out for a whole year. Now, there's many, many more watts than that. That's just a calculation to show you what this number sort of entails. So if you look down here at the lowest, this is the lowest amount of energy going in, 1.9 watts per square meter. Then it's 2.6, and then it's 4.5, and then it's 7.0, and then it's 8.5. So this is the amount of energy coming into the world from, say, we're looking at carbon dioxide here. So the annual amount of carbon dioxide per year is given over here. Way back a couple hundred years ago, it wasn't even 1 watt per year, per square meter per year. Now it's 40. Right now we're putting in 40 gigatons. I should have said it's not more than 1 gigaton. We're putting in 40 gigatons per year of carbon dioxide. So if I come up here and look at this, a gigaton is a billion. A billion is 10 to the 9th. They're talking tons of metric tons, which is 2,200 pounds. You can see this is a massive amount of stuff. Now they have a megaton for these other guys over here, which is the methane, the nitrous oxide, and the sulfur dioxide. Mega is a million instead of a billion. The carbon dioxide's coming on in billions of gigatons. I'm sorry. It's coming on in gigatons, which is billions of tons. So if we follow these 5 scenarios, one would be perfect. I mean, we're here, this is too much what we're doing, but if we could just reduce, we come out here, and you can see when we get out to 2100, we would actually be in the negative zone in terms of carbon dioxide equivalents, then that would be great. This is a pretty optimistic scenario too. If we're putting out 2.6 watts per square meter. So these are good scenarios. Even this one right here, we're still going up, but it's like we're getting things a little bit under control. So that would be, pretty good from where we're sitting right now. This is kind of like the business as usual. If we don't do anything, this is what it's looking like. So we could get up here, and that means in 2100 we'd be putting out 80 gigatons of carbon dioxide per year. We'd be doubling what we're doing now, and what we're doing now is more than we ever did before by far. So that would be sort of a disaster. And this is, I call this alarmist. I don't even know how we could get this much carbon dioxide out per year, but that's over 120, maybe almost 130 gigatons of carbon dioxide per year. The only reason you might think this is even possible, one is that the population's going up. It's possible we could have maybe 4 billion more people by 2100. And if they all are still trying to have a better standard of living, that might be a reason to generate more energy. But I don't think that would happen. Things would fail before we got that far. The other possibility is we pass a tipping point. Say we start releasing methane and carbon dioxide from permafrost and things like that. Then that could be another reason we might get up something so high as this. But this is not very realistic from what we're looking at. I would say these two possibilities are looking like the most likely outcome. You can see over here that methane could also keep going up. Nitrous oxide could. We're getting a lot of methane from fracking, natural gas wells and stuff leaking out in other places, rice paddies, cow farts, and things like that. So these are concerns, but the main one that we're looking at is over here. All right, so those are 5 different possibilities. When I look at the S there, I don't think of this complicated name. I just say scenario. Scenario 1A, scenario 1B, scenario 2, and so forth. Okay? So here, what are we looking at on this slide? Global contribution to surface temperature from different emissions with the dominant role of carbon dioxide emissions. If we look at this one right here, this is the SP1 where it's 1.9. So this is kind of like 1B. This is about the best we could hope for. I say it's actually, we're dreaming if we're going to get this. Currently, this is about what we've done. We've increased the temperature by about 1.1. If we maintain this particular level of emission, then it's predicted we would get this amount of increase. You could see we'd go up maybe 1.3, 1.4 degrees, and we could certainly live with that. If we could do that, things would be great. Now, if we come over here and look at the next level, so they're calling this, I'll say scenario 1B. I guess I called this 1B. This is 1A. We'll call this 1B. So is this possible? We'd have to act really fast to make this happen. But if it was possible, you could see we would still stay under 2, but we would go above 1.5. So here we are at 1. This is what could happen if we don't check ourselves. And a lot of that's going to come from carbon dioxide, you can see right here, and then a little bit from the non-carbon dioxide greenhouse gases like methane and nitrous oxide. All right. Land use. So land use and aerosols, they actually have that as a little bit negative. Now, if we just keep going like we're going, this is probably what we're looking at right here. And so we're sitting here at 1.1, and all of this would be extra temperature increase because we just couldn't control the carbon dioxide and so forth. Here's the carbon dioxide contribution. Here's the methane and nitrous oxide contribution. Here's a little opposite scale of the sulfur oxides and so forth. So this is a little too much. If we get over 2, then we are in trouble from things like tipping points and stuff like that. All right, so here we are again. This is a really bad scenario. Not likely, I think, for our world, at least in this century. Possibly in the next century something like this could happen. But here we are at 1.1 again, and this is all extra. And you can see a lot of the extra comes from the carbon dioxide that's assumed to be added in the future. This is what we're trying to avoid. And here's methane and nitrous oxide. This is also what we're trying to avoid. So again, the reason these might be bigger the way they are here is because of increased population. Adding 2, 3, 4 billion more people, that puts a big pressure on, energy, burning fossil fuels, growing food, things like that. And this is a nightmare scenario. If it's like this, then we don't have to talk about it or worry about it anymore. So I don't even think we should consider this one myself. These are predictions of temperature in 20-year intervals. So we're looking at year 21 to 40, year 41 to 2060, and 2081 to 2100. So these are each 20-year intervals. The best estimate, according to our little scenarios, 1A, 1B, 2, 3, 5, I don't know where 4 went. So the best estimates looks pretty good through 2040. All right. The only one that's really bad, goes up a little bit, is this one that I say that does not seem to be realistic. Right? So very likely range, if we stay here, is 1.2 to 1.7. We could definitely live with that. Our goal is 1.5, according to the Paris Accords, which probably we're not going to make. But this would be great. However, this is the one that we're hoping is possible. So if we could get, this 2.6 watts per square meter, that's what they call the radiative forcing. That's the heating pressure we're putting on the world from what we're doing. You can see it's still under 2. That's good. And these ones are still okay, but this is like right at the start. What we want to do is trace it out all the way over to the other side. So these are intermediate values here, and you can see each time we go up in the radiative forcing number, okay, then we get bigger and bigger numbers over here. The pressure to increase the temperature is greater and greater. If we go all the way out, well, let's look at this one because this is about 2050 right in the middle here. So this would hit about 2 if we don't change anything. Best estimate is 1.6, so we're still doing good. And then notice out of 2100 it starts to fall off if we can maintain that. Okay, if we can maintain this number here, then we're going to be better. And then this is the next possibility, which is still a little bit optimistic, but possible if we get our butts in gear. So you can see we go up a little bit. We're still under 2. So again, this is something we could live with if we can do this. This would require a lot of effort. You can see best estimate is 2 already at 2050 or so, if we're doing business as usual. So 2 degrees increase is not good. Right now we're living at about 1.1 degree increase, and you can look around the world and see what's happening. If we double that, then we're going to put a lot of pressure on all those bad things, the drought, the extreme rain, the ice melting, and fires, and all that stuff. If we go out here, we're almost up to 3, and 3 is something we never want to see. All right, this one is if we go crazy from more people, higher standard of living, we increase too much, then we're over 3, and now we're in big trouble from tipping points. we're not going to even consider this one. I don't consider that realistic. Okay, annual mean temperature is another chart in the report. Temperature change at 1 degree global warming. So what they're doing is they're considering the world's going up 1 degree. They're looking at the whole entire world and how the temperature is changing. And it's based on the color of the red that you see here. So they have a little chart down here, and you can see down at the very pale red or pink, the temperature hasn't gone up much. And you can find a little splotches in here where that's sort of the case. But this is these more darker pinks or reds are more in the 1 range right here. Now if you go to the poles, you'll see it gets darker because the poles are heating up about 2 to 3 times faster than the rest of the world. So this is just from a 1 degree increase, but the poles are going up a little bit higher. So if I look at that red right there, looks like maybe one of these, 2.5, 3 degrees or so forth. All right, now this is the actual observed. Over here's the simulated, and you can see it's pretty close. These guys look pretty close to the same. Now these are some other alternatives. What if we go up 1.5 degrees? And so you'll notice the reds get a little darker, and they spread over a little more area, and the poles are even darker than they were. And so here's the 1.5, the one that we were shooting for, if we met the Paris Accords, which it doesn't look like we're going to do. So if we hit more like 2, which is kind of where we're heading right now, you can see this is pretty dark. Okay, we're getting up here to quite warm, 5, maybe even 6 degrees up here. And so the Arctic ice is gone. This is in trouble up here. Greenland ice is going to be melting fast. So this is going to lead to some dire consequences, although some of those won't come about for 200, 300 years, say the Greenland ice and so forth. And then the one at 4 degrees, all I can say is this looks really scary. So I don't think that we're going to do that, certainly in this century. It's possible in a century or 2 that we could get up there. You know, that won't really be our problem at that time, but it'll be somebody's problem. Here's annual mean precipitation. So this is rainfall. Same idea that we're looking at here. So here's the 0 point, and you can see as we go sort of a brownish color, we're getting less rain. And as we go a bluish color, we're getting more rain. And so here this is the 1.5 degree global warming, you can start to see a little bit of the less rainfall showing up. Okay, as we go to the 2 degree, you can see that's sort of spreading out a little bit. And if we go to 4 degree, then we have that dark color all over the place. All right. So if we come down here, annual mean total column soil moisture change. So this is the soil is getting drier. Up here, this is the rainfall that's happening. So if the soil gets drier, then we're going to see more of the brown. And if it gets wetter, then we'll see more of the blue. So at the 1.5 again, that's kind of what we're shooting for right now. We would certainly like to get that. You can see there's still some drought areas showing up. Since I live in Southern California, I can vouch that we're getting a lot more drought here and fires that come with that. The soil is drying out, and it's harder to stop a fire with the dry soil and the vegetation. If we go to 2 degrees, everything gets a little more brown. There's a few areas that are still blue, like in the middle of Africa here. And if we go to 4 degrees, of course, that's going to not be good. Some areas like where the Amazon rainforest is, that's in big trouble. If that dries out, then it turns to savanna. We don't have a rainforest anymore. But that's even happening over here at 1.5. So this is kind of a funny little graph here. Okay, this is hot temperature extremes over land. So they're looking for really extreme, like heat waves and things like that sometimes come with fire danger and so forth. So this side over here is looking at once in 10-year events. Okay, so right now here we are. We're sitting at 1850 to 1900. Once every 10 years we get like a really extreme event, a hot, dry event. Now, if we go up 1 degree, what they're doing is they're saying, of these 10 right here, we're going to get 3 instead of 1. All right, so it's going to occur 3 times more likely if we're at 1 degree higher. And it does seem like we're getting more intense temperatures than we used to. But anyway, it's about 3 times more likely. If we go up to 1.5, which is possible even by 2040, it would be about 4 times more likely. If we went up to 2 degrees, it would be about 6 times more likely. And if we went up 4 degrees, it would be 9 times more likely. And so if we look at this 50-year period that we're talking about right here, 50 years, we would have 5 of these. And so if we have 5 of these 10-year periods, we would be talking 45 times having an extreme heat event. But let's say we stay down here. So 5 times this, 5 times 4 would be 20 extreme heat events over the 50 years. Now, even more extreme than 10-year event would be a 50-year event. So here we have 50 little squares. We're saying back here that this event right here happened 1 time out of 50. If we go up 1 degree, then instead of 1 out of 50, we'll get about 5 out of 50. If we went to 1.5, we would get about 9 out of 50. If we went up to 2.0, we would get about 14 out of 50. And if we went up to 4 degrees, we would get 39 out of 50 extreme events, 50-year extreme events. All right. So I think that's pretty self-evident there. This is the same idea with heavy precipitation. They just look at 10-year events now. So we're looking at extreme precipitation. Again, so they have 5 10-year intervals in 1850 to 1900. So this is just one 10-year interval with one event. And if we go up 1 degree, that's kind of like what we're doing now. Then we would have basically one event. So that's still pretty good, a little bit higher. If we go up 1.5, then we're looking at 2 events out of 10. And 2 degrees, 2 events out of 10, and 4 degrees, 3 events out of 10. These are extreme, intense, heavy precipitation events. But remember, we're multiplying that by 5. This is just 10 years. And if we had 50, we would have 5 of these. And over here, we would have 10 of these at 1.5. These are the agriculture and ecological droughts that we mentioned before. So these are drought periods. And again, if we're just looking at 1 out of 10, this is the extreme drought that we're talking about, the most extreme 1 out of 10. If we went up 1 degree, we'd have 2 of those. So over the 50 years, that would be 10 of those. And if we went up 1.5 degrees, it's still around 2. And if we went up to 2 degrees, it's still around 2. It's going up, but just a fairly small amount. And if we went up 4 degrees, then that would be 4 times, but that would be 4 times 5, or 20 very, very extreme drought events. We don't want that. So this is a different way that they look at things in the report. These are cumulative carbon dioxide emissions from 1850 to 2100. So we're looking at the full range up to 2100. And this is remember, this is the smallest forcing. This is the 1.9 watts per square meter times all the square meters of the Earth, which is, what was it, 5.2 times 10 to the 14th. So this is kind of like our reference point where we would want to be. And you can see this is the carbon dioxide going into the atmosphere in gigatons. Giga, remember, is a billion. So these are billions of tons of carbon dioxide, and you can see it's going into the ocean and the land. And this is good from the atmosphere point of view. The carbon dioxide in the atmosphere tends to heat up our world more. The oceans protect us from that, but the oceans pay a price. And that is they make acid, carbonic acid, when the carbon dioxide goes into the water. So there's a cost, but it does protect us from the intense heating that we're getting. Now, if we go to the the scenario 2.6, then you can see more the carbon dioxide is staying in the atmosphere. Okay, the oceans and lands went up, but the atmosphere went up more. Right, and as we go across, that keeps happening. If we go to the one that seems to be the direction we're on, you can see the carbon dioxide is going now almost 50%. So it's gotten more. As we go closer and closer to the very extreme possibilities, more and more of the carbon dioxide stays in the air. Even though these are going up relative to what they were, the percent of carbon dioxide keeps getting bigger and bigger the more and more energy we put into the world. So right now we are currently adding about 40 gigatons of carbon dioxide per year. All right. Now remember, if we go back about 200 years, we weren't even adding 1 gigaton of carbon dioxide per year. Now we're doing 40. So if we just kept that same rate and assumed we don't go up anymore and went out to 2100, that would be about 80 more years at times 40. That would be 3,200 gigatons more. Oh my gosh, that would be horrific. Okay, but what we're hoping is that we cut this down, ideally to 0, but at least cut it down a lot. Now the problem is I'm using 40, and actually the rate's been going up every year, and in fact this year it went up again. Even though we had COVID in the last year, the amount of carbon dioxide still went up. This is another projection that they put into the IPCC report. Global surface temperature change relative to our little reference point right here, this temperature. And so here's 1950. You can see a little bit above the 1850 to 1900 number. But it's pretty flat. And then we've going up about 1 degree where we are right now, about 2020. And so these are the scenarios. If we follow the low one, which I don't think is possible anymore, but if we followed that, the temperature would actually start to go down a little bit. Okay, if we went to the 1B scenario, we go up a little too much to come back down to 1, but we're still just maybe 1.5, 1.6. Okay, this is what we're shooting for. It's definitely under 2. Here's 2 up here. If we stay on the track that it looks like we're going to stay on, we would be up here, and that would be about 2.5 degrees higher in temperature. And we won't worry about these because we don't want them to happen. And I think people will have to respond someplace in here to correct. And so that should, hopefully protect us from these extreme areas here. This is the Arctic ice that's up in the North Pole, which keeps shrinking. Okay, this is back around, let's say 1960 or so, and there were 6.5 million square kilometers of Arctic ice in that area. But you can see over the decades it's going down, 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 and here we are right here. We're at about 4 million square kilometers of Arctic ice. That's going up and down, and every year it goes down, down, down. So the projections here, this is sort of inverted. The best projection would be we do not melt all the ice, and so we would still have some ice there. That's the 1A, 1.9 watts per square meter scenario. 1B, the 2.6, is still, we have some ice a little bit. Okay, so I'm assuming on this first one it's like 2.5 million. Maybe here it's about 1.9, 1.8 million. That ice is good because what the ice does is it reflects light. It bounces light coming into the Earth back out to outer space, and that protects us. If the ice all melts, then when the light comes in, it's absorbed by the water, and it actually heats instead of reflects. And so that's going to cause a bigger problem for our world. It's going to heat us up faster. This is the global ocean surface pH. Okay, pH is a measure of acidity. And the lower the number, we look over here at the pH numbers, the lower the number, the more acidic the environment is. In this case, we're talking about the ocean. All right. So again, you can see that the best scenario, which is probably not possible for us, is going to produce the smallest pH change. If we can stay at this one right here, which we'll have to struggle to meet this scenario here, but it is possible. We haven't passed it up yet. This is the one that's looking more likely. So if we look at this one right here, that would lower us to 8.0. That would increase the acidity by 35%. Right now, we've increased the acidity by about 26%. All right. So this is a lot. You're talking about, this is the environment of all these sea creatures and plants that are out there. All the life in the ocean has to live in that water. And we've just increased the acidity by about 30%. That's what we're looking at. If we were to go to those extremes, say we go to SP3, that would increase the acidity of the ocean by 218%. So, I just have a little question for you right here. What would happen if we did the same thing to your blood? That's the liquid environment that you live with. That's what we're doing to the liquid environment that all the sea creatures that are out there live with. So this can be disastrous, particularly for the corals. The corals are already suffering, and it may be too late for them. But in any case, that's what we're looking at for acidity. Global mean sea level. Okay, sea level, we're right at the start, so it's kind of small, but we've set it in motion. So in 100, 200 years, those guys are going to have a problem. But, we got to worry about the problems in front of us right now. So if we look at these different scenarios, again, it's sort of scenario 1A, scenario 1B, and 2, and so forth. By the time you get to 2100, it's still early because it takes a tremendous amount of energy to melt ice. But we're doing it fast. And so if we look at the, say, 1B right here, it looks like we might, if we can hold it right there, by 2100 increase, it's like a little over 1.5 feet. Okay, maybe 2 feet. The ocean's level, sea level will go up. Doesn't sound like much, but 2 feet, if you are a port city, what would be a port city? Say like New Orleans area or something like that, or Florida. 2 feet with a king tide, with a storm coming in, you're just going to flood the whole place out, and those are going to happen. So even 2 feet is kind of a drastic state of affairs. If we were to go up a little higher, even in 2100, we could almost hit 3 feet on the worst scenario. But again, we're not counting on that one. Now, they do actually have the possibility, say we pass a tipping point. Okay, say we melt the tundra and it releases methane and so forth, and we get a tremendous release of greenhouse gases. It is actually possible that the temperature could go up, something on this level here, over 1.5 degrees, 1.5 meters of sea level rise. And that would wipe out almost every coastal city in the world, plus rice-growing deltas like in Vietnam, the Mekong Delta, those would be wiped out. So I don't think this is going to happen, but it's those tipping points that make everything uncertain. It's the kind of thing where you say, I don't think it's going to happen, but it could happen. That's where we have to come into play. These are a whole bunch of factors. I don't want to go through them all, but you look up here, heat and cold, wet and dry, wind, snow, ice, and so forth in the open ocean. And so these are how things could change, number of land and coastal regions where they can encounter this problem. So I just picked out a couple. Here's extreme heat. Well, this says it's going to get hotter. This says cold spell. This says frost right here. It's going to get colder, and we're going to have fewer of those. Okay, this is more of them, and this is fewer of them down here. So these are decreasing numbers on the bottom and increasing numbers on the top. Less snow. Okay, that makes sense. The world's getting hotter. This could also be glaciers, ice, and so forth. Here's the ocean's more acidic. Okay, that's happening right now. So we'll get more of that. This is something I just highlighted here. As the water gets warmer, it holds the gas less well. And so the gas tends to leak out. And so you can think of a soda pop can. When you pop it open cold, there's still a lot of carbon dioxide, but when you let it set out overnight, all the carbon dioxide's gone. So there's less oxygen in the ocean, and this is bad for life in the ocean. So deoxygenating the ocean can cause a lot of life to die, and we don't want that either. And this is all based on a 2-degree global warming, which is what we don't want to see, but we might see. Okay, another chart of global surface increase is a function of cumulative carbon dioxide emissions in gigatons. So over here what we're looking at is temperature, so 0.5, 1.0, 1.5, 2, and so forth. These are degrees Celsius. Across here we're looking at cumulative carbon dioxide. Right now, with respect to where we started way back in 1850, we've added about 2,400 gigatons of carbon dioxide. That's where we are. And then this is projecting out with our different scenarios. So this scenario right here, the best one would be we add 600 more gigatons of carbon dioxide. Now there's a reason we don't want to go over 500, but if we add 600 more, then this is where we would be looking at in terms of temperature, And then if we added about, 900 more, 1400 more, 1700 more, 2000 more gigatons of carbon dioxide, then we're going to hit higher and higher temperatures. And we're not talking 2100 here, we're talking 2050. Okay, that's only 29 years away. All right, so 29 years, the worst case scenario, which we're not going to look for, would be 2 degrees increase by 2050. Well, this is what we're hoping for right here. By 2050, we don't want to see any more than 1.5. Right? But if we added more, say we added 900, then we'd see about 1.7. And if we added more, say 1400, we'd see almost 2 degrees Celsius higher. Okay, so these are the bad scenarios as we move up more and more. Cumulative carbon dioxide is what we're looking at here. All right. Now this time I'm talking, I already said if we went over 80 years, adding 40 gigatons per year. Here we're just looking at 30 years, so that would add 1200 if we stay exactly where we are right now, 40 gigatons per year, which we are going up every year, so it would be an effort to bring this down. But if we stay there, 1200 would take us to 30, let's see, what's at 1200 here? That would be around here, right around here. So that means we'd be about 1.6 degrees Celsius if we just keep going at 40. If we go more, then we'll be higher. All right, this is the estimates of carbon dioxide emissions remaining in the carbon budget. All right, so how much more carbon dioxide can we add to meet these different scenarios that we're talking about? So here's the historical cumulative amount of carbon dioxide. I said that was around 2400. There it is, 2390. This is the temperature that we've already seen. Like I said, that's around 1.1. So this is where we are. All right. Now, approximate global warming relative to the 1850 time. So what if we hit 1.5? Well, we've already hit 1.1. So that means we have 0.43 degrees Celsius more that we could get, that we could add to get to still stay at 1.5. Now, what's the probability of that according to the carbon dioxide we add to the world? Well, if we can keep the carbon dioxide to just 300 gigatons, we have an 83% chance of doing that. If we add 900 gigatons, then we only have a 17% chance of meeting the 1.5 degree limit. What about 1.7? Okay, well, if we can keep it to 550, then we have an 83% chance of keeping it to 1.7. But what if we add 1450? Then we only have a 17% chance of keeping it at 1.7. And what about 2.0 degrees Celsius increase? If we can keep it to 900 parts per million, then we have an 83% chance of keeping it under 2.0. But if we add 2300, and remember what I said, if we kept going, we'd add about 3200. If we keep it at 2300, then we'd only have a 17% chance of keeping it at 2.0. All right? So, remember what I said before. If we only go out 30 years at 40 gigatons per year, we'd add 1200 more. You can find that up here in the chart. If we go 30 years, if we go 80 years at 400 more, and then add 3200 gigatons, that's off the chart here. We don't have anything there. And so that's the end of my talk. I hope you got something out of it. I know I talked pretty fast, and hopefully didn't make too many mistakes.